Hello, everyone, and thank you for attending Lab Manager's Green Labs Digital Summit. My name is Mary Beth Didon, and I'll be moderating this discussion. Welcome to this session, The Path to Zero. Most of today's labs have a commonality in that they use traditional engineered control systems that have extremely high energy use intensity. Specifically, ducted fume hoods rely on continuous high airflow to contain contaminants, waste large volumes of conditioned air, and are energy intensive to operate. Filtered fume hoods employ highly efficient contaminant and filtration through either carbon filtration or high-efficiency particulate air, and at times, a combination of both, depending on the application handlings performed within the fume hood. Filtered fume hoods can also improve lab spatial efficiency by requiring less space between hoods and even reducing floor-to-ceiling height, as well as reducing the required space from MEP equipment, increasing the usable gross square footage. Their use enables sustainable lab design through several pathways: reduced ventilation makeup air requirements, minimizing conditioning and heat gain; reduced chemical and material consumption through more focused containment at the source; enhanced researcher comfort and productivity in labs with reduced air turbulence; increasing the ability for flexibility within the lab for the changes in the customer's workflow requirements; reducing the carbon footprint with average CO2 reductions of over 20,000 pounds per year. Please send us your questions or comments at any point during this presentation. Our speaker will address these questions during the Q&A session following his presentation. To ask a question or leave a comment, simply type your query into the Q&A box on the right-hand side of your screen. We'll try to address as many questions as possible during our time together, but if we run out of time, I will forward any unanswered questions to our speaker and he can respond to you directly if possible. Additional resources for this presentation are also located on the right-hand side of your screen in the handout section. I'd also like to remind you to answer our special poll question for your chance to win a gift card courtesy of Lab Manager. I'd like to remind you that the recording of this webinar will be available for free on-demand viewing after the conclusion of this event. And I would also like to extend a special thank you to our sponsors whose support allows Lab Manager to keep these webinars free of charge for our readers. So with that, I'd like to introduce our speaker for this presentation. Jesse Coro leads ERLab as Director of NA Operations, overseeing the company's strategic vision, product development, and operations. Founded in 1968, ERLab designs and manufactures sustainable ventilation solutions for the scientific research industry. Under Jesse's leadership, ERLab has emerged as an innovation leader in filtered fume hood technologies that enable significant energy savings for labs. Jesse has over 25 years of experience providing solutions to increase safety within the biopharma, pharmaceutical, medical device, and educational markets, with his specialty being focused on air filtration solutions for the protection of personnel, facilities, and the environment. Jesse's body of work includes USP 797 and 800 compliance strategies, developing sterile preparation and processing strategies, and environmental monitoring for aseptic processing. Jesse has also been assisting companies with their IAQ strategy and helping to implement solutions to create a healthier indoor environment inside and outside laboratories. Jesse, thanks for joining us today.
Thank you, Mary Beth. Truly a pleasure. Thank you, everyone, for joining. My name is Jesse Coro with ERLab, and for those who don't know, ERLab provides exposure control solutions for the protection of laboratory personnel and has been doing so since 1968. Today, we're really going to focus on sustainable laboratory designs and the differences between ducted and ductless filtering fume hoods and the overall impact. But I also do want to talk about the holistic approach to lab safety in a sustainable manner with filtered solutions. So as part of our agenda and the path to sustainable net zero laboratories, we're going to talk about, of course, why the push for sustainability, which many of us know, typical engineered control systems in place and how we can improve upon those and their overall impact to the environment, how ductless and ductless hoods can coexist together, and again, the impact of designing a lab not fully ducted, but with a hybrid solution of ductless and ducted fume hoods. And again, as I mentioned earlier, we want to talk about that holistic approach with filtration that we're able to provide in the lab, increasing safety in a sustainable manner. And I do want to touch and peel back the layers on the safety standards of filtered fume hoods and ductless technology, because at the end of the day, if this product is not safe, then there's really no need to talk about it, and the sustainability does not matter. And of course, I want to leave room for questions and answers. So why the push for sustainability? We all understand global warming is absolutely impacting our environment. Just look at the wildfires. They seem to be happening more and more frequently. It's interesting because Architecture 2030 called for a reduction of incremental reduction of carbon emissions. But for all new buildings and renovations by 2030. But in 2021, Architecture 2030 determined that the wait to 2030 was much too long. In order for us to meet that 1.5 degrees Celsius or 34 degrees Fahrenheit carbon budget, it was just going to be too late. So we needed to do something today. Today, cities and states and legislation are pushing for net zero and carbon reductions. And if they don't achieve that, if buildings do not achieve this in renovations and new build outs, they're proposing carbon taxes. And we should. I do want to point out this fact that laboratories account for 25% of the usable square footage in a facility traditionally. Yet they consume 66% of the organization's energy budget. Think about that. They have a significant impact on the overall facility and infrastructure, and that's why we're talking today about laboratories. And you're going to find out that ducted fume hoods contribute significantly to this energy burden. So types of carbon we're going to talk about today. We're going to focus on embodied carbon. What is embodied carbon? It is the CO2 emissions associated with the manufacturing of the product and the services. And then we're going to talk about operational carbon. This really has an impact on your total cost of ownership year after year and what the operational cost is going to be and the energy required to make these products run. So two different forms of carbon reduction, embodied and operational, and we will talk about both. Today, we deal with, obviously, a lot of ducted fume hoods, and I mentioned this a number of times within the laboratory. This includes biosafety cabinets and other engineered controls attached to the building's HVAC, but specifically ducted hoods we talk about. This is the tradition. This is the system we use as a barrier to protect us from the chemical emissions. The problem is ducted fume hoods consume a massive amount of air. They're starving the air handling units. We know the cost of energy has gone up every single year, and we saw a significant increase over the last 2 years, from 2020 to 2022, and even in 23, we've seen increases, upwards near 54% since 2006. So this cost is going to continue to rise. Therefore, the cost of air, the cost of energy is going to continue to rise. But that is not the only problem. Yes, the cost associated for sure, but we have to talk about, do we ever think of where the polluted air goes in a ducted hood? Not only are we throwing air out into the atmosphere, essentially dollars, but we're also throwing pollution out into the atmosphere. And when we're throwing this pollution out into the atmosphere and the stacks, you have to think about, where does that air go? The possible re-entrainment into the very same lab that you're throwing that air out of, or worse, an adjacent facility that may not even be a laboratory now has exposure limits. The EPA allows 100% of the threshold limit value to be released at the exhaust stacks. And you see on my screen, top right picture shows you what these exhaust stacks look like. Many of you are very common to this. EPA, again, allows 100% of the TLV to be released within 450 feet of the building. Well, again, how do you predict where air goes? And then they allow dilution to be a solution to the pollution. Well, unfortunately, that's not the way we need to think any longer. We need to mitigate the risk of that pollution factor being released out into the atmosphere. Then we look at the carbon impact. One 6-foot fume hood contributes to 22,000 pounds of CO2 in general. Now, that can vary depending upon how often that hood is operated, but in general terms, 22,000 pounds of CO2. So again, we got to think about this. And when I talk about the consumption, 65% of the building's consumption is due to the laboratories. This is the big reason why. And of course, exposure limits are not fully addressed because, again, we're adding exposure limits outside of the laboratory and possibly back into the laboratory due to re-entrainment. Now, when we talk about reducing the infrastructure costs, and of course, we know sustainability works on many different fronts. We have to look at the overall infrastructure. 100% traditional ducted fume hoods means you have higher construction costs and higher operational costs because you have to increase the amount of exhaust air, you have to increase the amount of supply air, and therefore you need larger air handling units, boilers, chillers, cooling towers, and exhaust fans. It's really a domino effect. They consume a lot of energy and a lot of air. We've already addressed that. But then if you're able to reduce the infrastructure cost by integrating filtered fume hoods, you reduce the overall operational cost and the construction cost. It's less expensive to build the building or renovate it. You reduce your boilers, your chillers, your air handling units. You reduce, obviously, your exhaust and your supply air. And a lot of people don't think about this. You can actually increase your square footage available for operations because you don't consume as much for the MEP equipment. So there's a lot, and there's a big impact here when you decide to design with filtration. So let's look at a traditional chemistry lab that's designed with 12 hoods that are ducted, 100% ducted, and the impact. And I don't want to go above anyone's head here, so I want to keep it in the simplest terms. When you have a lab and you're consuming air, you have to bring air back in. So you have supply air. There's a lot of calculations here. So you need supply air coming in for the air to come out so you don't create a vacuum. You need to replenish the air that's thrown out of these hoods. When you look at the exhaust air of hoods, you're looking at anywhere between 800 cubic feet per minute on the minimum setting and about 9,000 per cubic feet per minute maximum setting. So as those hoods are on and operational. So then you have to bring that in air in. That's the supply air. Again, you have 1,500 CFM minimum, about 8,700 CFM max. And you have to, the reason why it doesn't all equate here is because you add CFM for doors being open and things of that nature. But in simplest terms, what you bring out, you have to bring in. And again, as we mentioned, that is extremely expensive. If you look at the hood exhaust total here in air change rates an hour, minimum you're at 7, maximum you're at 34 air change rates per hour. That's a lot of air we're moving. So again, that's how a lab is impacted when you design a traditional chem lab with 12 ducted fume hoods. But what if we're able to take those 12 fume hoods and reduce those to just 2 of those hoods being ducted, 10 of them being filtered? How does this impact the laboratory? Well, we're able to reduce that min and max CFM quite substantially. Where actually you end up having a 7,400 CFM savings. Now, a cost per CFM, if I could put a cost on it, it is extremely variable depending upon where you are regionally. But on average, it's between $6 to $9 per CFM. So just factor that into quick calculation. So again, air costs a substantial amount of money, but you can see from these 2 slides the impact that ducted versus filtered has. Now, why do we keep 2 ducted fume hoods here? And that's a fantastic question that I just asked myself. Why do we keep 2 ducted fume hoods? Because we still need fresh air change rate. So these 2 hoods really aren't going to impact the lab much. You're still going to need fresh air as per code for proper dilution to bring fresh air in, especially in chemistry labs. So having 2 doesn't impact the amount of air needed. And it's just a safety buffer in the event of maybe you're bringing in a high volume of chemicals or things that you're just not quite sure of because you may be doing some research. So you can utilize those ducted fume hoods. And I'm going to talk about that in a moment further on in the presentation about what the capabilities are within filtered fume hoods and what our limitations are. And again, why these 2 ducted fume hoods may make sense. So let's talk about some case studies where we've actually integrated this solution and the results we were able to obtain from the installation of these filtered fume hoods. Now, I do want to point out Earlab has a exclusive partnership with LabConco. So you're going to see a lot of hoods here that may look familiar to you on the LabConco platform. And that's because they integrate our filtration technology onto their superstructure called Echo or Aero. And that's, when these larger scale projects, you're going to see a combination of that LabConco product with Earlab's technology and then Earlab's own what we call capped air structure. So I don't want to confuse anybody with the pictures. So let's talk about Bristol Community College. This is a great project. They were trying to achieve zero net energy in the Northeast Zone 5 climate, which is extremely challenging to do. The original design was ducted fume hoods, but they quickly realized that these ducted fume hoods consumed over half of the PV arrays installed. Therefore, it just was not going to allow them to achieve the LEED Silver certification that they were going for. So they had a value engineer and come up with a new design, and the solution ultimately ended up being 17 filtered fume hoods, reducing the facility's makeup air requirements from 70,000 CFM down to 24,000 CFM. Remember the previous slide. And then the MAP equipment reduction was down 14% of the overall gross square footage. So again, we left more room for gross square footage. We achieved ZNE with the help of other technologies, but ultimately filtered fume hoods ended up being the cornerstone, the linchpin to making this happen, but achieved zero net energy at $0 additional cost. Energy use intensity of just 51 kBTUs square footage a year. And therefore, again, we have more usable space, a more efficient laboratory, and ultimately a safer lab for everyone. As we were, again, designing this lab, they again, as I mentioned, high performance, that was the first design. And then we have the zero net energy design. And this just kind of shows you, goes into a bit of detail here of what a high performance lab does. And high performance labs are fantastic and they work. Again, the initial design was for this high performance lab with 22 ducted fume hoods. But the project, again, was put on hold because the president of Bristol Community College signed a 2050 zero CO2 challenge. When funds became available, the president of the school said that there was just no way to meet the challenge if they built the high performance design. They re-engineered the building, as I mentioned, to ZNE. And the high performance design required 3 air handling units at 70,000 CFM. Again, wasn't able to achieve it. So therefore, the value engineering, when they said, okay, we have to rethink this design. Let's go with the ZNE approach. How do we do that? Let's integrate filtration. And we went from that 70,000 CFM max peak to 24,000 CFM max peak. And of course, a lot of other technologies built in. But again, filtration being the cornerstone of that. As far as the energy use intensity, the EUIs, this is something that you have to see the overall reduction in a negative EUI in order to achieve zero net energy. It's a complex calculation, but to simplify it, it was designed at 290 EUI. So the energy use intensity as designed was 290. The high performance design reduced the load by 60 EUIs and allowed the design to achieve LEED silver. But by switching to the ductless hoods, they had a single highest reduction in load in building to achieve LEED platinum status, down to 110 EUI. So again, extremely significant. The additional energy saving measured in the addition of solar arrays, solar hot water collectors allowed the product to be at a certified negative 13 EUI positive energy. So this is just an unbelievable case study for us. Framingham State University is another great project. As far as sustainability, that was not the biggest intent here. It was really more about value engineering the design because of budgetary constraints. But ultimately, again, they designed it with 100% ducted fume hoods during the value engineering. The solution ultimately ended up being 49 filtered fume hoods, which resulted in a $330,000 net construction cost savings and an estimated $80,000 a year in operational cost savings. And again, it assisted in LEED silver certification. I do point this out, less dBA noise. Noise is pollution. These hoods are extremely quiet as compared to ducted systems, and we actually reduce the noise level wherever we integrate these hoods in a laboratory, which is important as well. Lafayette College is another great case story for us. I know they keep coming, but it's important to know. This was 11 hoods, 11 filtered fume hoods. And again, they set their goal for the facility to reduce energy consumption by 45% below the LEED baseline. The project was designed to meet LEED Gold, but really they wanted to go better. The college climate action plan had pledged to reach carbon neutrality by 2035. So they wanted to be better than LEED Gold. The result ultimately, again, 11 filtered fume hoods. We replaced an inefficient biology building, resulting in a 40% reduction in campus CO2 emissions, 74% reduction in energy usage compared to the 2030 baseline. So again, significant savings. This achieved LEED Platinum certification and AIA CODI Top 10 project in 2021. So has significant value. This one, Northeastern University, it's in the process of being commissioned as we speak. We just completed the installation of fume hoods. Now everything's being certified. But this was a new 350,000 square foot state-of-the-art research center. The project housed 71 ducted hoods with the capacity of approximately 32 more. The project also housed 77 filtered fume hoods for the chemistry teaching lab. That's what we just did the installation, and it's being commissioned. Those 77 filtered fume hoods eliminated 50,000 CFM exhaust. Previous slides, again, remember the impact. And then therefore, 50,000 CFM of fresh air. We removed 260 tons of chiller capacity. Houses consumed with air conditioners on about 4 tons. We eliminated 990 gallons per minute of pumped chilled water and eliminated 990,000 BTUs of boiler capacity. Again, the cascade effect. This just has a significant impact again. The HVAC eliminated by using the filtered fume hoods. Again, I mentioned that earlier, but it just shows you the boilers, the air handling units. It's just massive reductions. You can't achieve this with other technologies. This is why ductless filtering fume hoods are so important to spec into new designs and new lab build-outs to see if it's the right solution for you because of the reductions that we're seeing. We look at the 20-year operational carbon footprint. You look at 20 years, if all these hoods were ducted to 77, you're looking at about 24,000 US tons. Now that the 77 hoods are filtered, we reduced that down to 1,485 US tons. So again, the proof is in the number, the energy, it's all in the energy savings and the reduction. The Butler University, another case study, the original scope. Now they are a recurring customer, an unbelievable advocate for the technology because they just did another redesign, another renovation in which we installed an additional 25 hoods, give or take 5. I don't know the exact number, I forget, but I'd say another 25 fume hoods. The scope of the original project was 30 fume hoods, 12. And then as they increased their capacity and knowing that, hey, we have other pieces of equipment here and other areas of concern within the laboratory that we need to provide containment for, they actually installed 12 more capped air enclosures, which are our other enclosures for the rotary evaporators. They installed 2 filtered storage cabinets and a whole room air filtration, which is the Halo. Again, reducing the emissions, protecting the breathing zone through filtration. At first, the project was again, designed with 26 ducted fume hoods, and we had to look at the cost structure. What is the cost variation between ducted and filtered, and my operational cost. Ultimately, we ended up saving $116,000 on first install cost. That was the construction cost. The fume hoods, the upgrade to the building's infrastructure, the supply, the exhaust, all takes into account the $680,000. And then with the filtered fume hoods, it's about the fume hood only because you don't need to upgrade the controllers, the exhaust systems, anything like that. So that zeroed out. We're at $572,000. So the savings was $116,000 up front. But then we look at the 10-year operational cost savings, and this is, again, where it becomes extremely impactful. You look at the ducted fume hoods at 744 CFM per fume hood, 26 fume hoods, that's 19,000 total CFM. Annual cost on that with the $5 cost per CFM is about $96,000. So the 10-year operational cost is almost $1 million versus that of a filtered fume hood with replacement, taking into account that you have to replace the filters, was about $390,000 over 10 years, $39,000 amortized year after year. That's a savings of $577,000. Now, there is a caveat to this. They did not replace their filters until the 5th year of operation, and they just kept testing the filters. They sent them off to Pace Analytical to run T-clip testing to see if there was any leaching. There wasn't. They couldn't get the filters to break through, so they kept pushing them. Weren't getting breakthrough with our sensors. We weren't detecting anything. They weren't detecting anything with their portable GCs. So they kept pushing the filters. So this cost savings that you see in this screen actually goes up exponentially. And again, one of the many reasons why they continue to purchase filtered fume hoods. And this just shows you the design impact. So this is what the HVAC design would have been: the supply work, the main supply, the exhaust duct work, the main exhaust duct work. This is what it would have looked like with 26 ducted fume hoods versus without. So again, we reduce the complexity of installation, reduce the complexity of design. We reduce the embodied footprint because we're not using so much metals. We're not using so much transportation, that cascade effect. So that's all the case studies I have now. We have many more, but that's all I have in this presentation. So are fume hoods really safe? And this is a question you absolutely should ask. The answer is yes. There are standards we have to adhere to. There's 4 standards that I want to speak about today. ANSI Z95, NFPA 45, CSA Z316, and AFNOR NFX 15-11. AFNOR 15, NFX 15-11 is one of the most important standards for filtration efficiency on a filtered fume hood. And I'm going to give you a quick 101 on what this standard really means. And again, peel back the layers on this standard. But what's very important to know are these numbers. Detection accuracy. Now, ANSI Z95 has written into their standard that you can have exposure no greater than 25% of the TLV re-entrained back into the laboratory under emergency conditions. AFNOR says we want less than 1%, which is critical. We don't want 1% of TLV. After that, we consider our filters to be saturated. And this is going to make more sense to you when I talk about the AFNOR standard. Again, ANSI says 25%. We obviously have to adhere to ASHRAE 110 contaminant standards and AFNOR XP X15. And of course, we have to look at NFPA 45 and see what do they reference. NFA 45 points to ANSI Z95. ANSI Z95 actually points to AFNOR NFX 15-11. CSA says it should be a fraction of the occupational exposure limit that's released at emergency situations, which becomes a little bit more complicated. But at the end of the day, they all point back to this AFNOR standard, which is very critical to understand and to ensure the safety of these hoods and ensure that we don't have re-entrainment back into the laboratory. One other thing I do want to mention is the layers of filtration. They all require redundancy. AFNOR has 2 different layers of filtration, class 1, which is redundancy layers of filtration, and class 2, which is only 1 layer of carbon filtration, which we don't do often. That's more for high school type of chemistry, very low volumes. Majority of our customers go with the 2 layers redundancy. And again, that's as per code as well. So ANSI, NFPA, CSA, if you want to meet those standards, you must have 2 levels of filtration and of course, continuous and automatic breakthrough detection as well. So are they safe? They are safe and they do adhere to standards. So let's talk about that AFNOR standard, which many of them point to. As I mentioned, it is the standard for filtration efficiency, but it does encompass the products in its entirety as far as containment efficiency and airface velocity. But let's talk about the filters and the efficiency of the filters. So AFNOR is very complicated. First, in order to adhere to AFNOR NFX 15-11, you must have a published chemical listing of the list of chemicals that your filters are able to retain. More importantly, you have to know down to the molecular gram of those chemicals that you can retain before we've seen release no greater than 1% of the threshold limit value at the filter's exhaust. How is this test performed? Well, as you can see here on my screen to top right, we test these filters in a hermetically sealed chamber so that we capture release at the source and without dilution, and we have mass specs, GCMS is tied to the top. Again, we're getting real-time release, so we know exactly what our capabilities are for this published chemical listing booklet. Now, you don't see it here. You see a picture of it, bottom right, but it's a list of over 750 chemicals, which are tested under 6 different concentrations twice. It represents thousands of chemicals. There's a lot of detail that goes into this. Because we've done this testing and we continue to test, and we know byproducts, we know vapor pressure, there's a lot involved in this testing. We're able to provide a feasibility study of the handlings which are performed within that fume hood to determine first, is filtered fume hoods the right solution and applicable for your specific application. And then after that, and we say it is, then we provide you with an overall life cycle of the filter so you can get a total cost of ownership of what your true realized savings are going to be. And again, that life cycle is our guarantee that throughout that process, there's never going to be release exceeding that 1% of the threshold limit value. I'm going to touch on that in a second. And then, of course, we have to have third-party validation. So when I mentioned that filter life cycle, went ahead of myself. This just gives you a quick snapshot of what that chemical booklet looks like. Again, chemical name, the CAS number, the vapor pressure, You'll see the TLVs, the TWAs for different countries because we are a global company, and then the overall retention capacity with our filters for that specific chemical. So again, now tying back to the conditions in which we determine the filters to be feasible for your specific application. I mentioned a filter's life cycle. Traditionally, filters last 24 to 48 months. That is variable depending upon the type of application, but most of the time, I say 80% of our customers, our filters are between 24 and 48 months. That's at which point we consider it normal operating phases. We have to adhere to 3 separate phases: normal, detection, and safety. So again, normal is at which point we've said this filtration is right and suits your needs. And then the longevity of the filter is going to be 24 months. We have to guarantee throughout that 24 months that they'll never be released exceeding 1% of the threshold limit value. But then we have to have two other conditions we have to adhere to: detection and safety. And this is at which point you see this diagram to the right. This shows you the layers of technology built into our filter stack. Now, depending on the size of the hood would determine how many of these stacks are integrated into the hood. Traditional 6-foot fume hood would have 4 of these stacks. So you can imagine there's a lot of filtration going on in these fume hoods. We also have the capability of integrating HEPA filtration and carbon filtration. So what you see here in this diagram is a layer of HEPA filtration, a primary level of carbon filtration, a fan module, and a secondary level of carbon filtration. Very important to know. This primary level of filtration is the workhorse. This is the filter that is going to capture, obviously, the majority of all the chemicals that are be using within that fume hood. This fan module is also a sensing chamber. So this is where we're going to detect any spikes of concentration past this primary stage of filtration. And that backup redundancy layer is there in the event we do detect a spike in concentration. So what happens if we do detect a spike in concentration? Because we have that secondary level of filtration, we still guarantee that even at detection phase, there's no release exceeding 1% of the threshold limit value in a class 1 configuration. So that's 2 levels of carbon filtration. If you only have class 1, we guarantee it 50%. But class 2 is what we go with most of the time. Then we have safety phase. Safety phase is at which point this hood's gone into alarm. It's now detecting concentration past that primary stage of filtration. And now you've had a spill in the hood. This is at which point we consider the hood into safety phase, and we still guarantee that there's not going to be release exceeding 50% of the threshold limit value for 1/12 of the filter life cycle. We never want a hood to get into safety phase, and they should never get into safety phase because we have backup redundancy where we constantly manage all of our customers' accounts to ensure filters are replaced according to the lab's analysis and recommendation, and obviously the sensors that are constantly built in there as a reminder that, hey, we have breakthrough and you want to replace your filters. If you go into safety phase, you have to look at the administrative controls, and you have to have better administrative controls into place. There's absolutely no reason for that to ever happen in the hood. But in the event it does, we do have protection built in. I want to talk about residency site for a moment. So with molecular filtration, unlike HEPA filtration, with molecular filtration, breakthrough can happen abruptly. So you look at a parking lot at Christmas time, there's less parking spots. So where do people go? On the curbs, on the mediums, on the snowbanks, wherever they can find a spot. Molecules act the same way. If there's not a spot to go, they're going to find a spot. And sometimes that spot is outside of that filter. Therefore, it releases, and then it goes into that safety redundancy filter. This may happen on occasion. You may get a blip, a spike. If that happens inconsistently, there's really no concern. It's when it happens continuously. That means that we have constant breakthrough, less residency sites. The molecules are not finding a parking spot. And now we're using a precious residency site within that secondary level of filtration. And that's important to know. We don't want to do that because when we replace the filters, this primary filter gets disposed of. This secondary filter rotates down to become the primary. The new filter becomes the secondary. So we don't want to use up residency sites in that secondary filter, reducing the longevity of the life cycle when you rotate that filter down. Now, just as much as we know our capabilities, we also know our limitations. And it's what you see on the screen here. Noble gases, chemicals which are naturally gaseous under normal temperature and pressure conditions. Those are our limitations. And of course, we have the not recommended. We have mercury because it's well retained, but we don't have a means of great detection. Hydrogen cyanide because it's immediately lethal. Obviously, perchloric acid because of crystallization and you need a washdown hood. Acid digestion and radioisotopes. After this, it's about the quantity of chemicals that you're using and the quantity that's being evaporated. Now, there's times where we run a feasibility study and we determine at first glance there's things we need to do to reduce the overall evaporation. Well, we use an Erlenmeyer flask. Maybe we can use a vacuum pump. Maybe we can keep a container closed during the operations more frequently. That bath that's used in the hood, maybe that can be closed for the most of the time. Again, reducing the overall evaporation load. So there's times where we work with the customer, we go into detail and we say, okay, we need to change X, Y, and Z chemical to this type of handling. Can it be reduced? Are you overestimating? There's a lot of things we do on the back end to work with our customers to perhaps get them to use filtered fume hoods because they know there's just such great value behind it. But if you're using any of these chemicals, there's no way for us to work with you. It's just, this is what have to be handled in a ducted fume hood. Now, all of our products have what's also called smart technology built in, and this is part of that detection phase process that I spoke about. All of our hoods have a smart light common theme built into our products, and that's an indicator of the product's performance, whether it be a halo for whole room air filtration, a storage cabinet for at source containment, or a fume hood. That light indicates product performance. That light's steady, you know the product's operating at peak operational performance. For a fume hood, if we've seen air face velocity reduced, that light's going to pulse, followed by an audible. If you've seen filter breakthrough, again, detection phase, that light will pulse, followed by an audible. If we've seen a ventilation failure, light will pulse, followed by an audible. It's also enriched with a web-based platform where you can either direct connect the product to the unit to get real-time data feeds of the performance, or you can tie it into the IT infrastructure, or we have what's called a nano router, so you can have near-fi capabilities and just easily connect to the product. This also keeps a data log, so it can help improve overall laboratory practices. In the event that you're seeing sashes are left open continuously at a certain time, you can address that situation to say, hey, Joe, I see that every day at 3 o'clock your sash is opened. I know this because I see it through this platform. Let me talk to you about the importance of containment. And we need to have 100 feet per minute so that we have the best barrier for your protection. So again, there's a lot of value built into this product. So what about disposal? Since we're talking about sustainability, I know this question is going to come up, so I'm just going to address it. What happens when you dispose of the filters? Do they go into the waste stream? No. Proper means of disposal is incineration. Now, when you incinerate a filter, now we've run T-clip testings and we know these can be properly incinerated. Incinerators also have to adhere to strict EPA guidelines, much like the AFNOR standard. For every 10,000 molecules, only one molecule could possibly be released. They have their own filter stack, possibly released at their stack. So what happens with our filters? Well, they go through this incinerator, they go through the process, they help contribute to the 14 megawatts of electricity these incinerators can provide. Again, that's clean electricity from steam that's generated, create clean flue gases. So not many people know these generators do that. One of our filters contributes to 24 kilowatts. So again, there's value in all of these filters. Again, we want to create that zero carbon footprint. So then when it's incinerated, one filter will equate to 3/4 of a cup of ash. Then that ash is put on the conveyor belt and then brought to the landfill. And here's the EPA guideline, the 264343, for these specific incinerators. So in summary, filtered fume hoods in general are the cornerstone to achieving ZNE goals. We know that. There can be a balance of ducted and filtered fume hoods, and in times it's encouraged to do so based on handling and air exchange requirements. We must all do our part in saving the environment. We have to. The good news is that we can, and we can achieve this without compromising safety, most importantly. And 4, look for ways to improve current inefficient engineered controls, because I'm sure you have a lot of inefficient systems in your laboratory, maybe not, but the majority do. And there's ways to look at your facility, do an assessment, and determine where can I make improvements. So with that, I would like to thank everybody. This slide obviously says, visit me at booth 905. We're not at a booth, but I'd like to thank everybody and leave it open for questions and answers. Thank you.
Okay, great. Thanks, Jesse, for a wonderful presentation. So at this point, we are ready to move into the Q&A session with our audience. Again, for those of you who joined us late, you can send in your questions or comments by typing them into the Q&A box located on the right-hand side of your screen. And one more reminder to please check out the handout section on the right-hand side of your screen for supporting information about this event. Jesse, thanks again. Let's jump right into the audience questions. We have this first one here that says, how do you meet safety standards for a fume hood?
Sure, I addressed that on the slide. So we adhered again to that ANSI Z95, the CSA 316, AFNOR NFX 15211, and NFPA 45 2023. So we do have to adhere to all those in addition to ASHRAE 110 for proper containment and airface velocity.
Okay, great, thanks. Let's move on to the next question. This one says, what are your means for detection?
Great question. So in that, you saw that filter diagram. In the fan module, we have what's called the dry contact metal oxide sensor. And really what it is, we code it with the millivolt setting based on the prominent breakthrough chemical. As soon as that potential is modified within the millivolt reading, that indicates that that specific chemical has been detected. Each chemical is coded with a certain millivolt. As soon as that's detected, we detect at ranges between 25 to 50%. But again, because we have that redundancy level, we still have that guarantee of no release exceeding that 1% threshold limit value.
All right, great. Thanks so much. Here's another question. This one says, is it possible to use filtration for formaldehyde handlings?
Absolutely. We do that often. We work with a lot of histology, pathology labs, and we can use filtration at source, which is important with formaldehyde because it is a heavy molecule. It's hard to draw formaldehyde up, so we can create downdraft tables, back wall systems, or more importantly, put it into a containment device such as an enclosure. So absolutely, and we do have a means of detecting formaldehyde as well.
All right, wonderful. Thank you. This next question says, will filtered hoods impact the balance of the room air?
They will not, because we do not tie to the HVAC system. We're not taking any air out. We're just processing the same air over and over again. So there's no impact on the balance. There's no impact on the humidity conditions. Temperature is minimal. Our largest hood consumes 260 watts. That's our 6-foot fume hood. So again, any heat load generated from our fume hoods is extremely minimal.
All right, great, thanks. We have some more questions coming in. This one says, how are chemicals validated to ensure there is no risk of exposure?
So that was the feasibility study that I mentioned. We have to, it's a very detailed process. We have to understand the chemicals used, the quantity of chemical, the type of container the chemical is in, if there's any heat load associated with that, to determine whether or not, and of course all the chemicals collectively used within that fume hood, what potential byproducts can exist. And then that analysis is performed by our lab, our team of PhD chemists, to determine feasibility and then determine the overall filter life cycle. So basically understanding what the overall retention capacity is going to be within those filters for all of those chemicals.
All right, great. Thank you. We have another question that says, what if we use a filtering fume hood and have a spill in the hood? Are the filters able to handle such events?
They are. That's part of that safety phase. And again, we take a lot into consideration. Even when we're validating, we take into consideration spills. And if a spill does occur, are we going to be able to handle that spill? That's part of that safety phase. That's part of AFNOR NFX 15 to 11. And then, of course, we have to look at the possible potential of LELs when there's a spill based on the chemicals handled within that fume hood. So the answer is yes, and that's only because we run that study.
Wonderful. Thank you. We have time for a few more questions. This one says, you mentioned other filtering systems. Can you tell me more about the ceiling mounted system? How big of an area will it treat? And will it also provide filtration of bacteria, mold, and fungus?
So, all right, so we'll start. That's a twofold question. The first one is the area of treatment. The Halo will treat 1,000 square feet of space, so 10,000 cubic volumes of air, and add an equivalent known as an EACH, an equivalent air change rate of 1 for every Halo. That's on the carbon side. It's designed to capture fugitive emissions of any chemicals present in the lab without the need to add additional air change rates through the HVAC system, because we know, again, that costs a lot of money and it's not sustainable. As far as bacteria, mold, fungus, things of that nature, general pollution, we will integrate a HEPA filter, so an H14 HEPA filter, and we'll have the same volume of air treated. We have studies on both chemical side and the viable and non-viable side of particles to see the overall load concentration reduction. And in those spaces, we're seeing on average anywhere between 70 to 90% reduction of concentration.
Great, thank you. Here's another question. This one says, are the storage cabinets NFPA rated?
So the storage cabinets, our own that we design, no. Those are just for our general organics and solvents. And as far as flammables, we have a system called the ChemTrap. And perhaps I didn't show that, I apologize, but that's a system that sits on top of a NFPA rated flammable cabinet. And it connects to the bung port on the back of the system, processing a very low 45 CFM continuously so that we don't allow concentration to exist within that cabinet. Therefore, when that cabinet door is opened, the lab technician is not inundated with those high concentration loads, which can impact them quite significantly. We've had technicians tell us that they've passed out and doing rock, paper, scissors. Whose turn is it to open up this cabinet today? Because it is very risky. So we do have a system that goes onto NFPA rated units.
All right, wonderful. Thanks. We have time for one last question. This one says, would you be able to provide a cost analysis if we are looking at a renovation project so we can assess the true value and ROI?
Yeah, absolutely. Because there's many variables involved, we do have a calculation formula that we use, and we can give you a very close baseline as to what the savings are. And then in that baseline, we also factor in the filter costs, because we have to. We obviously don't want to hide that. So we give you a total cost of ownership of the product and a total cost savings, including what's needed for filter replacement.
All right, wonderful. Thanks so much, Jesse.
Thank you.
This brings us to the end of this webinar. On behalf of Lab Manager, I'd like to thank Jesse Corll for all the hard work he put into this presentation, and I'd like to thank all of you for taking time out of your busy schedules to join us. A reminder that all of the presentations from the Green Labs Digital Summit will be available for free on-demand viewing. Please watch your email for a message from Lab Manager once these videos become available. Once again, thank you to our sponsors, Erlab and PerkinElmer. Their support allows Lab Manager to keep these events free of charge for our readers. Please be sure to tune in for our next presentation at 11 a.m. Eastern tomorrow, Building Sustainability to the Lab. For more information on all of our upcoming on-demand webinars, or to learn more about the latest tools and technologies for the laboratory, please visit our website at labmanager.com. Thank you all for being part of our Green Labs Digital Summit, and we hope you have a great day.